153 is a sum of the cubes of its own digits. Can we find similar numbers in other bases? It turns out we can, using a familiar polynomial identity. Let's start with the pattern that we have seen before. It keeps going. 16, 50, and 33, all cubed and added, gives 165033. And 166, 500, and 333 do it again. Here is the central claim of this video. These are not three separate coincidences. These numbers have a name, which are known as Armstrong numbers, and they're just seen in different bases. First, what does a digit even mean? In base b, a three-digit number equals d2 times b squared plus d1 times b plus d0, where each digit is anything from 0 up to b minus 1. A three-digit Armstrong number in base b means a number equals the sum of the cubes of those digits. Now, let the base be 100, where a single digit is anything up to 99. Take the three digits 16, 50, and 33. We'll draw each digit in its own box. As a base 100 number, because each digit is exactly two decimal digits, the blocks simply concatenate to give 165,033. Notice that this is exactly equal to 16 cubed plus 50 cubed plus 33 cubed. So, the number we started with is a genuine three-digit Armstrong number in base 100. Another instance of this pattern is in base 1000. The digits here are 166, 500, and 333. The same pattern holds again. The cubes add up to exactly the original numbers concatenated together. This gives us a three-digit Armstrong number in base 1000. So, where do the digits come from? Let's put the three rows in a table. Divide each base by 6 and round down, and we get the leading digit. Half each base, and we get the middle digit. And divide each of the bases by 3 and round down to get the units digit. Let's state this as an identity in general and ask the question, for which bases b does this identity hold? What do 10, 100, and 1000 have in common? Every one of them leaves a remainder 4 when divided by 6. In fact, every power of 10 does. So take any such base and write it as 6k plus 4. Then a sixth of b, rounded down, is exactly k. A half of b is 3k plus 2. And a third of b, rounded down, is exactly 2k plus 1. In base 6k plus 4, our candidate has the digits k, then 3k plus 2, then 2k plus 1. For k equal to 1, that is 1, 5, 3 in base 10. Now, let's prove it. Cube the digits and add using the sum of cube expansion on 3k plus 2 and 2k plus 1. Combining the like terms, the cube sum is exactly 36k cubed plus 66k squared plus 42k plus 9. Side 2 is at the number that the digits spell in base b. With b equal to 6k plus 4, b squared is then 36k squared plus 48k plus 16. The leading digit contributes k times b squared. The middle digit contributes 3k plus 2 times b. And the last digit adds 2k plus 1. Adding the three lines, we get 36k cubed plus 66k squared plus 42k plus 9. This is the same exact polynomial we got as the cube sum. Therefore, the two sides are equal for every single base of the form 6 times k plus 4. Hence, we have generated an infinite family of Armstrong numbers in bases of the form 6k plus 4. The only edge case is k equal to 0. That would be base 4, where the leading digit is 0. So, the family starts at k equal to 1, which is base 10 itself. Setting k equal to 1 in the shared polynomial, and we do get 153, which is the Armstrong number that we would have expected. One more in the base programmers actually use. 16 is 6 times 2 plus 4, so hexadecimal gives us a 3-digit Armstrong number with k equal to 2. The formula we derived before says the digits are 2, 8, and 5. In hexadecimal, which we preface with OX, we get 2 times 16 squared plus 8 times 16 plus 5, which is equal to 645. Now we cube the digits. 2 cubed plus 8 cubed plus 5 cubed also gives us 645. Therefore, we have found a 3-digit Armstrong number in base 16. So, line up the family of 3-digit Armstrong numbers. We see them for base 10, base 16, base 100, base 1000, and 1 for every single number that is of the form 4 mod 6. Hence, we have discovered infinite bases with 3-digit Armstrong numbers. Therefore, one polynomial identity gives us a 3-digit Armstrong number. If you like these videos, please make sure to like and subscribe for more.